Hi friends, welcome to another one of these. This is me answering and explaining the STAV 2021 Unit 3 and 4 trial exam. As per usual, when we do these things, you should have both the exam and the solutions with you, and ideally a cheat sheet as well, because you might want to update it. You might want to pause and just add a few things to it or cross something out, or just a page of notes so that you can write down a few things as I say them. There's a lot of anecdotal information that's going to come out of my mouth that isn't written here. So it's worth being ready for that. All right, let's get into it. So, multi-choice. Now this is every answer to every multi-choice question on this test on one page. So if you don't believe you need my explanations, if you just want to see the answer in my little mini explanations here, just pause this video now and read through it. Obviously, I'm about to explain every single one of them, so let's do it. Question 1. That number on question 1 is expressed as two significant figures, best given as scientific notation, right? See, there are two that are correct. A is also correct. 46 is the best way to say it. But scientific notation guarantees that the 4.6 by 10 to the 7, excuse me, is narrowed down to two significant figures. The 46 could be exactly 46. It could actually be 46.00000, right? And if they just say 46, you don't know whether it's about 46 or exactly 46. But scientific notation implies that it's been brought down to two significant figures. So it's a very technical term, but that is the best of the two answers, and the other two are simply wrong. Question 2. Digital stopwatch can record to the nearest 100th of a second. Forgive my cat in the background. And is used to measure, that one, yeah, and is used to measure an event time to be 2.19 seconds. Which of the following best represents the result? They're testing your knowledge of error of devices, right? The error of any measuring device is half the least count of the device. So in this case, the least count of the device is 100th of a second. So half of 100th of a second is 1/200th of a second, which is 0.005. So the answer is B, 2.19 plus or minus 0.005. Okay, question 3. Which one of these things is the most likely contributor to the uncertainty of that, excuse me, of that time recorded for the winner of the race? All of the things that they've listed do contribute to the uncertainty, but the biggest contributor is B. Okay, they all contribute. But the variation in range of readings obtained by the different timekeepers, the fact that 5 different people are going to hit their thumb in 5 slightly different times, and they're going to be random errors, they are going to be bigger errors than any of the other 3. So that's the main contributor to the error. Question 4, you either know this one or you don't. The variation in times given by the 5 timekeepers using manual stopwatches is best described as random errors. It's random because you don't know whether someone's going to click the button early or late. And if they do it early one time, they might do it late the next time. It is totally random. Question 5, do you know your variables? All right. When measuring this race event, there are several variables involved. They list them there. Which of the following best describes the independent, dependent, and identifies one possible control? The independent variable is what you change. We're changing the distance, right? So each time we run this race, we're going to do it for 100 meters, then we're going to do 200 meter races, then 50 meter races, whatever. We're going to measure the time, so that's the dependent variable. And in each of these things, we're going to control the age. Everyone involved in the race will be all 15-year-olds or all 13-year-olds or whatever. Okay, so they are the 3 best answers. And that option was A. Question 6, this is measuring the force between 2 objects. In this particular case, they're 2 electrical charges. There is a fairly standard formula for this. It's pretty much the same formula for the gravitational force between 2 objects as well. The letters are different, but the arrangement is the same. Right? It's some constant times something about the 2 things. In the case of gravity, it's m1, m2, it's the 2 masses, and then divided by the distance between them. In the case of electricity, it's the charge on the 2 charged objects divided by the distance between them. Same deal though, right? I'm not going to insult your intelligence by walking you through the calculation. You know how to do this. You needed to calculate it. Make sure you get the units right. They've been nice to you here. They've put everything in meters and coulombs, which is what it should be in, and the answer turns out to be B. Okay, question 7. A couple of metal plates are connected to the terminals of a 2000 volt DC power supply, DC. So one of them is always plus and one of them is always minus. Right, which one of the following statements is true? The first one's true. Right? The electric field direction is always away from the positive plate and towards the negative plate. All right. So they gave you one arrow on that diagram for the electric field direction. So the top must be a positive and the bottom must be a negative, and that's pretty much what A says. The top plate is connected to the positive terminal of the power supply. That's right. Question 8. This is a flat-out test of whether you know this formula. Right. So I don't believe this one is actually on the formula sheet. You might want to just check that. I don't have a formula sheet with me at the moment. You might want to check if this particular formula is on the official formula sheet. If not, stick it on your cheat sheet, all right? This is how to figure out the gravitational field strength around a particular object of that mass at that radius from it at any time, okay? These are the measurements of the planet in the middle, the thing that's causing the gravity, not the thing that's being attracted by it. So if they tell you that there's a 4,000 kilogram satellite floating around Venus, what's the gravity on it? The mass is the mass of Venus, okay? And the radius is the radius of the orbit around Venus. It's got nothing to do with the radius of the spherical satellite or something. It's what's causing the gravity. Okay, so they're just testing, do you know this formula? Do you know how to apply it? The answer turns out to be D, easy enough. This next one is a little bit harder. This is something that a lot of students get wrong. This is one of those physics questions that a lot of smart people never understand how to do. So if you can get how to do this, you're going to put yourself ahead of thousands of people. This is a good one to know. All right, so we're going to spend a little bit of time on this one. Astronomers observe a planet in a nearby galaxy to be twice the mass of Earth and also twice the diameter. The gravitational field strength on the surface of this planet compared to Earth's G value would be which of those four options? All right, so here's the best way to do these things, where you're comparing one to another, right? Where you get a lot of questions like this, and it doesn't necessarily have to just be about this formula, it can be about any formula, right? But when they give you a situation and then say, oh, here's another one that's twice as big and 4 times as far away or something like that, you know you're going to do this. Start with what they give you first and just call everything 1. All right, so let's just say that the Earth's radius is 1, the Earth's mass is 1, and that value of capital G just happens to be 1. You could waste your time actually calculating the real number. However, it would just be a waste of time. This is going to do the same job and you're just playing with ones. It's as easy as pie. So just assume that the Earth is 1, right? And then they said this other planet is twice the mass of Earth. So for this other planet, you just put a 2 there, twice as much as 1, and twice the radius. So you put a 2 down there, twice as much as 1, and figure out what you now get. Right? The Earth's G was 1 here. This new planet's G is going to be a half, so the answer is a half G. And that was B, which is why the answer is B. That is by far the faster way to do it. The other way to do it involves actually putting in the value of G, the value of the mass of Earth, the value of the radius, right? And then doubling those two and doing it all again. Don't waste your time. This is a really good shortcut. Question 10. Okay. Magnetic fields are dipoles. They go from a north to a south, or on the inside of a magnet, they go from a south to a north, right? So as soon as this question said that the field is created by a monopole, it can't be magnetic. It also can't be gravitational because a gravitational field attracts towards something rather than pushing away like this one is when you look at the diagram. So it has to be an electric field. That's the only thing it can be. That has to be a positively charged object pushing other positively charged things away from it. So the answer has to be B. Question 11 is just checking whether you know the right-hand group rule. They've given you a wire going that way, and they're asking you to describe the magnetic field around that wire, and of course it does this, right? It comes out of the page above and into the page below. If they had said electron flow, right, it would have been left-hand rule, same deal, right? But you would have gone like that. So you would have gone X's on top and dots on the bottom instead. But they just said current, so you go right-hand rule. So the answer is C. There are dots on top where it's coming out of the page, right? The wire is my thumb, and crosses on the bottom below. You either know that one or you don't, and that was literally just checking, do you know the right-hand grip rule? Questions 12 and 13 are both about the same thing. They're both about a transformer. Again, you've been given a diagram. It's got a fair bit of information in it, so stop for 15 seconds, do yourself a favor, and just look at the diagram before you read the question. All right. So it's clearly a transformer. It's got two different circuits coiled around one side, coiled around the other side. That's a transformer. It's a step-down transformer, left to right, because there are more coils on the left than there are on the right. And there's 240 volts on the left, and there's a resistance of 18 ohms on the right, but they haven't told you anything else. All right, now that we've had a look at it. Okay, it also says just before it, just above it, a transformer is being used to step down 240 volts AC to 12 volts AC, and they're both RMS. All right, the secondary side of the transformer is connected to a resistor. Okay, no surprises there. Right. 12. The ratio of the primary side coils to the secondary side coils is the same as the voltage ratio. Right? So they just told you that 240 goes down to 12, so 12 is 1/20th of 240. So the voltage ratio is going to be 20 to 1, and so that's exactly what the coil ratio is, 20 to 1. It's not 1 to 20. You've got to get this one around the right way. Right? So question 12, the answer is B. Now this is a reasonably easy question, question 13, because they asked you for the RMS current, so you didn't have to worry about multiplying things by √2 to get peak or peak to peak or something like that. They kept it all in RMS, which is great. So concerning the right-hand side of the transformer, you've got a resistance of 18 volts, so 18 ohms, pardon me, and a voltage of 12 volts because they told you it's stepping down to 12 volts. Right? You just use V equals IR to find out what I is. Turns out to be 0.67 amps. Which is C. Easy enough. Question 14 is about diffraction patterns and is about de Broglie wavelengths and all that sort of stuff. If electrons and photons are passed through the same crystal, the observed diffraction patterns are very similar. This indicates which of the following, this is what it indicates. Right? The same diffraction pattern has to be caused by the same wavelength to gap ratio, basically. So it's probably these. So given that they're the same gaps, they're both going through the same crystal, they must both be the same wavelength, right? So D says the photons and the electrons have the same wavelength, right? If those two things are the same, or if the ratio between the two of them is the same, you get the same diffraction pattern. So you just had to reverse engineer that little fact. Question 15 is the same sort of thing, excuse me, or it's in the same area. A double slit experiment is set up. They've given you the diagram there. They've given you all of the figures that you need. It is literally asking whether you know how to use this formula, right? Which is normally delta X out the front, but I've made the wavelength the subject of it this time because they're asking you for the wavelength in question 15. Watch the units. The only thing they can fool you on here is the units, right? And you'll notice that all of the answers start with 6.25, right? There's 625 nanometers, 6.25 nanometers, 6.25 by 10 to the minus 9 meters. They're all different, but they all look very similar. So make sure you get the units of everything that you put into the formula right, and make sure you understand what unit it comes out, and it should come out in meters. All right. The answer is actually D, 625 nanometers. So your calculator is likely to give you an answer of 6.25 by 10 to the minus 7 meters. So you need to understand that that happens to be 625 nanometers. So if you don't, let me know when we get back to school together, and I'll remind you of a couple of tricks about that. Question 16, it's another factual thing. You either know it or you don't. When light undergoes refraction, which one of the following things changes? The only thing that changes is the wavelength. The waves get a little bit shorter as a wave front travels like this and goes, let's say that that's the boundary between air and glass, for example. If waves go into glass, they slow down. So this one slows down first, and this one's keeping going fast, and then this one slows down as well. So the wavelength starts off bigger and ends up smaller because they all sort of catch up to each other. It's a bit like traffic slowing down and the cars getting closer to each other as the traffic slows down. And then they speed up again when they go out from glass to air. Everything else is the same. The frequency stays the same, the amplitude stays the same, only the wavelength changes. 17 and 18, these are a bit tricky. This is another one of those areas. It's a little bit like this question here, where a lot of smart people don't know how to do this question, right? So you need to become a smart person who does know how to do this question. All right, 17. The answer is D, and here's why. Right, so it says, which of the following statements is true in that circumstance that they've drawn for you where there is a car going around the side of a corner? Excuse me. As it goes around the corner, pardon me, kinetic energy is a scalar quantity, so it doesn't have a direction. So as you change direction, as long as you've got the same mass and the same velocity and the same speed, pardon me, your kinetic energy doesn't change, even though it's a half mv squared. And I know velocity is a vector quantity. Oddly enough, energy in all of its forms is a scalar quantity. So if you have 100 joules of kinetic energy going that way, and then you have 100 joules of kinetic energy going that way, your energy has not changed. Right? It's a scalar quantity. Momentum is a vector quantity. So as you change direction, your momentum changes. So this car was going around a corner, it's changing direction, so momentum does change, kinetic energy doesn't change, and that's what D says. Question 18, if I had to bet which one of these questions most people got wrong, I'd say question 18, right? And I'd say most people said the wrong answer. Most people have said C instead of A. So this is a classic Newton's third law thing. The force that's keeping that car in the circular path is definitely C. It's directed towards the middle of the circle. But that's the force on the car. That's not the force by the car. That's the force of the road on the car, right? The road is forcing the car to get around the corner. The car is trying to force the road in the opposite direction. The tires are trying to push out in the direction of A on the road. It's a bit like when you walk, you push the world backwards and the world doesn't go backwards and you go forwards instead. That's Newton's third law. Every action has an equal and opposite reaction. The action in this particular case is the tires trying to push the outside of the road towards the outside of the circle. The reaction is the road failing to become loose, right? And instead doing the opposite, the equal and opposite thing to the car and giving it a force in the direction of C. And that's what makes it go around the corner. Obviously, if that was a very loose, gravelly road, C wouldn't be possible, and the car really would go in the direction of A and slide off the road and crash into a tree. Right? But a lot of people are going to get that one wrong. Most people would say C, but the answer is actually A. Question 19's got a couple of things about it that might annoy some people. It's just a bit more complicated than it has to be. Okay, spring has a spring constant of 250 newtons per meter. There are two of them on this thing, an identical pair of these springs are placed next to each other and 10 kilograms is stuck on it. Right? The compression of the spring is best given by, okay, so we're going to find out how much the spring compresses by. Right? So the last thing we're going to do is use this, right? F equals Kx. X is the compression of the spring, K is the spring constant, and F is the force pushing it down. Right? So that's what the last thing we're going to do. Firstly, we don't know what the force is yet, so we're going to have to calculate that. So the first thing we're going to do is this. Right? The force on the spring is just the mass times the times 9.8 of the 10 kilogram bunch that's on it, right? Which is 98 newtons. So there's 98 newtons pushing two springs down. So because the two springs are sharing the load, each spring is experiencing 49 newtons pushing it down. Okay. They gave you the spring constant. They said it's a spring constant of 250. So 49, 250, what's X? Right? That's what you do. And you figure out that X is closest to 20 centimeters out of all the guesses they gave you. And that's why the answer is D. Question 20, this is worth me drawing a diagram for you here. So here goes. Ground, ball. Okay. Says Ben's traveling in a car. At the moment he passes Nicholas, who is standing on the road, right beside the car. He drops a cricket ball out of the car window. Which of the following statements is true? Okay, so I'll draw Ben in green. I'm sorry, Nicholas in green. So the guy on the side of the road, Nicholas. There's Nick. Right. If the car was still, the ball would just go hit the ground straight down. But the car is moving, and therefore the ball is moving when it's let go. Right? And so it's not going to do that. It's going to do this. And that's what Nicholas is going to see because he is stationary. Right? If it asked, by the way, if the question had asked what Ben sees, and you know, part of the answers are about what Ben sees, Ben is going to see the ball drop straight down, because as the ball does that, Ben's head does this, because Ben's moving along with the ball in the, you know, in the car. Right? The ball's dropped outside the car, but Ben and the ball are going that way at the same speed. Right? So while the ball goes downwards and across at that speed, Ben goes across at that speed as well. So the horizontal component of their motion is basically not noticed by either of them because they're the same. They cancel each other out. So Ben just sees the ball get further and further away vertically. Neither of those answers, or neither of those answers about Ben, excuse me, say what really happens. He won't see the ball hit the ground behind him. He'll see the ball hit the ground directly below him, right? Assuming no air resistance and all that sort of stuff, right? So they didn't mention air resistance, so we normally don't assume it's there. However, the one true thing is what Nicholas sees, and that's D. Nicholas will see the ball go in a parabolic path. He won't see it go straight down because he's lagging behind the ball. All right. Sorry, the number was C, pardon me. I thought it was D. The answer is C, parabolic path. All right. Okay, folks, that is the end of the multi-choice questions. I'm going to save this file now and start the rest of this in another file. Thank you.